Hey everyone, so nice to meet you for the last time in this mini course. So today we're going to look at the proper deep learning models using convolutional neural networks, and we'll see how they work in detail. We'll implement them step by step. So let me know in the chat. So as we are not meeting in person, only online, so we can use the YouTube chat. So can you hear and see well, plus minus in the chat? If there is any problem, let me know. I see one plus in the chat. What about others? Two pluses. We have only two people ready to work. Like, if you will skip this last session, you will have to do this yourself and be harder. Either if we work together, it will be easier. So what about others? Can you confirm that you're ready to work? Meanwhile, I will open the first task for today so that we would have option for you to download the template. Again, remember that I think the Windows users, some of you had some problems of downloading Python files. So be aware of that, that you could use the some other tools, so like from the command line or whatever. So, but I also will try to quickly compress the template. I just forgot about that you have the problem. So I will compress the templates. Just a second. We'll compress them in zip files while I'm waiting for the answers in the chat. And that way, there will not be problems for Windows users to download files, because that Windows some things that those files are dangerous, even though they are not dangerous. So anyway, just a second. So that will be a zip file at the end. Okay. So the classwork, image classification template, convolution 2D function .zip. So 6.2 template should be now open. We'll also update the homework template. So 6.2 is open. Okay, sorry for Martins who is out of the class today. Anyways, you can catch up later. Anyways, but it's easier for those who are online. So it seems really not a high like engagement this morning, but okay. So yeah, so the template 6.2 is available. And now let's jump into the Jamboard for a while. So this is the model which we will build today. So you can, like, in a very like abstract level, you could think that the Tesla like self-driving car, the image classification models work in a similar way as this. So that you have these convolutional layers, the nonlinearities, ReLU layers, which you already know how to make. You already had to do that. Then pooling layers, and then a fully connected layer, which is the linear layer, which you also know how to make, and the probability distribution with the cross entropy and the softmax, which you also know how to make. So the only new things here are the convolutional layers and the pooling layers, and there will be some additional layers as well. So this will be the model what we will make, and the logic behind is following. So let's start by examining data, the algorithm, and then the code, and then we will do the coding. Oh, sorry. So before we start, I wanted to I'll give you an update on the marking of the course, because this is super important. If you want to get past this course, you must have over those in between like 40 or 50%, then you would pass the course. But basically that would be really bad the mark, but still you would pass the course. So right now the situation is that like for this morning, on this morning the best score was for Muhammad, then Martins. But I also have a serious warning for Muhammad and Sharil. Basically, I found at least one work where you copied from each other, and like if I will find that again, I will just give a 0 mark next time. So please do not do anything like that again to try to copy the code from each other. So then also so those people who don't understand how to code, I assume that that might be this part of the yellow part. So then please submit the homework classwork so that at least you can pass this course at some capacity. And those of you, so the last very important stuff here is that if you want me personally to be your thesis supervisor, so basically if you want to work on some serious machine learning research for your thesis, so that you could get like really good work or publish something in scientific papers, so then you must have 90% and up the score here. So if you can get 90% of the course score, then I'm okay of being your supervisor for the thesis. Otherwise not, because this course is like super simplified version than in other universities. So this is like the most simplest version what this could be possible now, because otherwise I usually do like these small tasks that we do together to give them as a task to the students, where I explain the algorithms and functions, and then they implement themselves, not just write with me together. So this is the situation with the course. So basically you have a 2 weeks about like 2 week time to get either those like to the mark what you want basically. So that's for the situation, 2 weeks, and then you will get the mark. So here, let's then return back to the course material. So today it's really exciting material because we're working with the actual proper deep learning models. So let's see where we have it. So we will work with the interesting dataset first of all. The dataset is apple so the fruit classification task. You will have a dataset with images where there's different types of apple, and the different types of apple have different classes, right? So this is like Granny Smith, Golden Delicious, and so on. So you'll have those images, and those images will be in RGB format, right? So the red, green, blue format, so that you have 3 channels per image. So well, it's actually a matrix. So if we are talking about like grayscale matrix, then we would have just one channel, right? If that would be a grayscale, that would be black and white image, it would be just one channel with the width and height dimensions. But now this is a color image. That means that we have three separate 2D matrices put together with the C dimension, channel dimension, which is 3-dimensional image, right? Because it's actually 3 colors here. So if there would be like alpha dimension, which is like transparent parts, then would be 4 dimensions. The depth dimension or any other dimensions, it would be also more dimensions. So that's the data set where we are going to work today. And of course the output. So this is input, of course, right? Input. So, and if I'm not mistaken, it was like 100 by 100 size image or something like that, but it's not that important even. I think it is like 300, something like that. And so that's the input. Of course, for the input, remember that the first dimension will actually be batch dimension, so it's actually four-dimensional image, four-dimensional kind of like input for the model, and then the output will be the batch comma class count. So how many classes of apple do we have here? And oh, I don't recall it, so we'll just need to check it. Just a second. I will also check the dimensions of the X. So if you download the dataset, you should be able to see it already. I mean, if you download the template and try to run it. So yeah, it's 100 by 100. So that's one, right? 100 by 100, and then the class count. So there's something. So the class count is 5. So there is a 5 Apple classes. Oh, it's actually nice that this picture also have 5 Apple classes. Anyway, so that's the plan. So, and of course, the output of 5 classes, what it actually means, just to remind you, is that like, so if you have like a vector, so let's try to write it here. So if this is the y prim vector, which is the probability distribution of which class does this apple belong to. So what it is actually, it says that, let's say this is 30% this apple, 30% this apple, then let's say 20% this apple, then 10% the honey crisp, right? So, and then 40% 40% golden delicious, and then 0% this pink lady, whatever. So this is what we want to predict, right? And of course, it will be not in the percents, but like 0 0.3, 0 0.2, 0 0.1, 0 0.4, and 0. So this is the task. What the model, this artificial neural network, this convolutional neural network should detect. So looking at the image, what is the probability of which class this image belongs to? Like, is this a golden delicious apple when I give the yellow picture of an apple, or some other kind of apple? So in this case, the input probably is, if we would have this kind of probability distribution output, then what it means that the input image is actually this guy. So the red delicious would be this one, which goes inside here, like in this format, inside the model, and then after the model you get out this distribution, and it says that, okay, if I give you the image of red delicious, then this is actually red delicious. So that's from the data point. We will look that also in the code. And then from the model's point of view, so the model is kernel function. So the kernel function just means that there is some kind of mathematical function which you can repeat or execute in parallel to all of the data points in any kind of set. So it can be some data set, can be some set of feature maps, and so on. So basically, the linear function, in terms of one sample, takes everything as at a point value. But the kernel function, so it repeats the same function many times. So I will show you like comparison actually. So this is like an idea of convolutional neural network, but originally it came actually from a little bit different angle. So let me quickly find some image. So fully connected neural network. So originally, in the early days, when they tried to build these models, they tried to build the models just using the fully connected layers or linear layers, not using convolutions. Also for the image tasks, of course. So like, I don't know, maybe I can just give you some example. Okay, I don't. I will just write it. So because otherwise I don't like the inputs. So anyways, the old way how they did it is using fully connected layers. So here you also have the FC, the fully connected layer, the last one. But originally, what you could do is to just use multiple fully connected layers with ReLUs inside them, like between them. And you could theoretically do the same thing. Oh man, I don't know why I cannot copy them. Anyways, that's strange. So if I would add not like this, but like this, like some, I don't know, like 4 FC layers, which are linear layers, which we already used last time when we had the used car examples, where we try to predict either the price or the transmission type of the car. We just used multiple fully connected layers with the ReLUs in between. So the idea is you could also make a model where you put this input here. So in order to put this input here, the only thing you need to do is to reshape it. So reshape, so flatten basically, flatten. So if there was batch channels width or in height, or height and width, whatever, like it's height, width and height, you could flatten it just to dimension batch comma everything else. So C multiplied by V multiplied by H, and then you would have just a one-dimensional data point, or like in this case two-dimensional with a batch, which you can easily pass through the fully connected layers one by one, and then produce as an output this class distribution, right? So you could do something like that, of course, in the red arrows inside there, and then the output, right? There is also ReLUs or sigmoids or something like that. If you just put like linear layers one by one, it doesn't make sense. So so there is a ReLUs, and also here there is a ReLUs. So anyways, we could do something like that, and this was what the scientists did in early days. But first of all, this kind of model is huge, because like if you have like 100 by 100 by 3 dimensions, this already is like in hundreds of thousands, if not millions. So let me check. So 100 by 100 by 3. So yeah, so this is in this case it's a 30,000, but there is also batch dimension, so it just makes really large number of calculations. So it takes a huge memory, especially in old days. So instead, the Jan LeCun, which is one of the most important scientists in deep learning, yeah, I think it was Jan LeCun. So he's from France. Yeah, Jan LeCun. So he published some paper in, I think it was like in early 90s or somewhere about that time, and he proposed to make the convolutional method, where you use the not fully connected layer to all of your data set, all of your data point, like all of the image, but split the image in many small parts and then apply kind of the fully connected method, or the dot product, matrix multiplication by dot product for this small region on the image, and repeat that many times and produce many feature maps depending on, so you can basically define the number, how many you want, and then afterwards basically you reduce the number of parameters by a factor of 10 or even more. So it's much simpler, and then later on, so like when the researchers looked more at the convolutional neural networks, they discovered that they actually, those kernels have all sorts of very nice properties. So they basically, these kernels are like small filters, and they create those filter maps which kind of resemble actually what the human eye would see in the retina, basically. you know, like the eye neural network retina. So let me find ConvNet features. So just want to give you some image which I forgot to find before. So there are the kind of features of the elements that these neural networks, these convolutional neural networks, learn by themselves. So nobody tells this model that it should learn those features, but it does by itself. So, and those features actually look really similar. So if you would look at neural, actually brain research, where they research the neural way how neurons work in brain, especially in the retina, in eye, which the visual cortex system of the brain is one of the most complicated in the brain. So here there's an image there. So if there is a first layer after applying those those kernels, you would get feature maps which look something like this, where the idea is that you can see that they look like a Jamboard patches. So this is actually something that people did a long time ago when they first start using convolutions, that they manually try to make these kind of features. So it's detecting kind of straight lines or corners or blobs and stuff like that, and then slowly it accumulates more and more features until it kind of starts understanding that this is a wheel, for example, or there is maybe a door or something like that. So it starts to combining more and more features together, making it more semantically meaningful. So that, and it does it completely automatically. So it's not something that you kind of encode in the model, but it learns how to do this automatically. There's a lot of materials on the internet where you can find really nice examples. So anyway, so that's so far. And then yeah, so let's keep digging in. So the kernels itself, how they work and how they look like, and also visually, there's one of the materials that I gave you in the preparation materials for today is from the Stanford University. They have really nice animation. So anyways, here there is one of the methods. So actually the edge detection kernels and sharpening kernels and all sorts of median filters, or even like there's a lot of types you can do with the kernel functions, and all of those are like you can do also those manually. So these are manual ways of applying those kernel functions. So these are like pre-built functions, like where you have pre-built kernel matrices. After applying those to the image, you can see that you get some modification, like extract some specific features from image. You can also make them the dynamic, for example, median filter or something like that. And in our case, we will learn those kernels. They will not be something that we predefine, but model will learn using backprop this kernel. So, and the way how you apply the kernel is something like this, and I will show also animation, which will hopefully help to understand it better. So, the idea is that you go with a step, like a stride size, like every second pixel or every third pixel with the 3x3 kernel in this case, and calculate the so you multiply all of those values with each other with the original input picture, and then sum them together. So you sum plus all of them together. That's a very simple way how to do that. You can use of course also dot product if you have multiple dimensions, which in this case is that if you have multiple feature maps at once. So here, again, the same idea. So, and you move this kernel along all of the image slowly and create the new feature map, basically. So let me show you another way. So I'm just trying to, I found a couple of images. I'm really not sure which one explains this the best. So that's why I'm just dropping all of them. And then I will show also the animation, and then we will do this in code, and hopefully at the end it will be made clear. It will be clear basically. So the idea is here that we multiply one by one those values, then we sum them all together, then we insert that value in the new matrix, and we repeat this for like many times, like for one feature map, and then for the next layer, and then so on. So it slowly, actually, if you configure it properly, it slowly reduces the size of the output image. So if you had like 100 by 100 input image, maybe the output image will be 80 by 80, and then slowly 40 by 40, and so on. So, but at the same time, maybe you would like to increase the dimensionality, because in the very beginning you have only three-dimensional input where you have the RGB channels, but at the end maybe you want this to be more, you know. So anyways, we'll find quickly the where was that material which I like. So I think this one. Yes, this is actually from the same place. They had a really nice animation, I think. Oh yeah, this one. So I like this one. Let me see. Yeah, so here there is actually, so this material is available in the 6.1 section where I added the materials for today. So the idea is that you have RGB input channel here. So these three maps here. Then you have two filters. So you have filter W0 to filter W1, and you repeat the same operation for with each filter. So if you pick filter W0, you go by all of these feature maps one by one. Then you multiply them, and then you sum everything together, and you add also bias if you want. Bias is optional actually, but you can add it, and then you store it in this new matrices which comes out. And as you see that the new matrix which comes out is smaller than the blue part here. So the green part is output and blue part is input. And you can see that input was 5 by 5 and output is 3 by 3. So and here if you add the padding, then it's actually 7 by 7, but basically the input is 5 by 5. And in this way you kind of exchange, you kind of compress the features. So you can think that with this example we compressed the size of image to smaller image, and we also compressed the feature dimension. So there was three-dimensional, now we're getting two-dimensional. So we're kind of extracting and compressing all of the necessary features and trying to learn them so that they would represent the high-dimensional, high-order features which we like to classify, like is this an apple of Golden Delicious or some other type of brand. So that's something what we're trying to do here. Okay, so definitely look at those animations. Okay. So far so good. I think the last thing before we start coding and looking at the code is that there is also one specific interesting way. So as you see that there is 5 by 5 input, and then we get 3 by 3 output. And if you think about it, there's definitely a way how to describe this process as a formula. So if I have, like, let's say 5 by 5 input, and I have kernel 3 by 3, and I have, in this case, stride, I think it's by 2, yeah, it's so 2, so the stride is 2 and padding is 1. If I have all of those parameters, I can calculate what will be my output size. And this is very important, because if you think about it, if you go back to this slide, if you don't know what is our output size of this image, so this is our input size of image, then it's after some of the convolutions it becomes smaller, right? And if I don't know what is at the end this size of this image, there is absolutely no way I can do the fully connected layer here and then predict some 5 classes out here. So I need to keep track of size. I need to calculate what will be the size of applying this kernel function. And luckily there is a function how to calculate the size which will come out of the kernel function. And that very simple function is this one. So that will be also something you will implement. So, and here let's look at one-dimensional example as well. So in this case, in the previous examples, we looked at two-dimensional examples, right? But just so that this would be simpler, we can look at one-dimensional. So this is basically exactly the same thing as this. So here we have a two-dimensional image with the zero padding around, right? And then the kernel moves here, and we calculate the output. And in this case, this is just like one slice of it, right? One small slice of that two-dimensional image. So let's examine this example where we have the kind of input. It's interesting that the input and output is the same. So this configuration is very common in convolutional neural networks, because if we just, for example, not go one step by stride one, so in this case, the step is one. Step and stride is the synonyms. So, but if we would go by stride 2, then the output will be smaller. But now, because it's going just by stride 1 and there is a padding of 0, it really nicely aligns so that the output is exactly the same. And just to verify that this is true, we can check here these parameters. So let's see. So the kernel size, which is the most simplest part, right? So the kernel size is 3, because you see that the kernel, this blue guy, it's only three-dimensional, right? So there is a three-dimensional, I mean not three-dimensional, but the length is 3 for the kernel. So that is that. Then the padding in this case is 1. So we see that we add zeros in both ends. We can add more, or we can add 0 as well. So there is no rules for that. Then stride, in this case, the step size is 1. But if we add stride 2, then we will get smaller output, which is sometimes good, actually. And we often use that kind of approach as well. So these are those input parameters. And then we also need n in, which is the input of size of that orange part. And the orange part size is that, basically, if you look at it, it's 8. Yeah, I hope it's 8 size. Yeah, so anyways. Then here, if we do the calculation, which is again very simple, so n out is, so there is the n in, so that will be 8 plus 2 times 1 minus 3 divided by stride, which in this case is 1. If there would be a step size or jumping with the size of 2, we could actually, let's do the same calculation for the Stanford image, like this example as well, just in a second. So stride divided 1 plus 1. So let's look what we have here. So this is 8. So there is a 10, 7. Yeah, so this will be interesting, I think. Yeah, so it seems like, yeah, so it's the 7. Yeah, 7 plus 1. So, okay, if there would be a stride of 2, then this would not divide equally. And in that case, it would just skip the last, so it would not go over the last padded element. And it would be also fine, because if it's just padded, then basically it doesn't care that we don't include it really. So in this case, the output, of course, is 8, the same size as an input. So this is really common configuration with kernel size of 3, padding 1, stride 1, and you get the same output as the same input. So now let's look at this example. So I will try to copy this one to the Jamboard, and let's calculate using the same formula for this example. So let's drop this one here. And you will implement this formula in code just a second. So again, the idea is that we need this because we need to keep track of size of the kernel, of the feature maps, because at the end we want to do the linear layer. And in linear layer, if you remember, this is just a matrix dot product, the matrix scalar multiplication, and in that case we need to know what are the dimensions of that matrix, like the width and height of that matrix. And if we don't know that, we cannot do the last matrix multiplication. That's why it's important to understand how to calculate that. So here, let's look at this example. So in this example, we see what is output already. So this is really nice. So we can double check if the formula is correct. So in this example, the n input is, if we look here, the blue parts. So the blue parts is 5. Then the kernel is, of course, the same as before, 3. And it seems like that the stride is 2. I think the stride is 2. And the padding is 1. Yeah, so was there also, I think nothing else necessary. So n out then is the 5 plus 2 times 1 minus 3, and then divided by 2 plus 1, which is then the, so there we get the 7, 4, 4 divided by 2 plus 1, which at the end is 3. So you see, the formula works. So if we had the blue input of this 5 by 5 image, then applying the convolutional function, which goes by stride or step, basically jumping over, if it starts here on this part and then immediately jumps two columns ahead on this part, and then again jumps 2 columns ahead on this part, then we get this nice output. And yeah, so this is basically what it is. Okay, so let's jump into code. So please get ready your template from 6.2 tasks. So the code looks like this. We'll zoom in. There are a few interesting things that we will discuss as well. So one interesting thing is that we will use today Google Colab. So remember, I told you about this already. So Google Colab. So I will write down. So in order to use GPU, the graphics processing unit, for faster training, you will need to use Google Colab. Or if you have the GPU on your own computer, everything will be great. So anyways, the Google Colab is the way how to do this for free on internet. So basically the idea is that what it says here is that if Torch CUDA, the GPU like library, is available, so in case if you don't have GPU, NVIDIA GPU on your computer, you would not be able to run this on the NVIDIA GPU. So, but in case if you're running this, for example, on Google Colab, which I show you in a minute, so not in a minute, but a little bit later. So basically, then you can use CUDA, and it will work much faster. So all of these operations, like the kernel function, which you repeat many times, of course, you can do that at the same time in parallel, and those are very small functions. So that means that the GPU processing unit, which have like a huge number of cores, and they can process very small operations. So they usually use it for like applying the shaders or applying the lightning to the polygons, or calculating the transformations for vertices, which is also, all of these are like very fast kernel functions. And basically you can do the same or using the machine learning functions, and that's why GPUs are super useful, and every like machine learning scientist use GPUs. So basically this is the way how we define. We either use the device CPU or device CUDA, so now there is a constant, and then actually how to use this constant is super simple in Pytorch. In Pytorch, the only thing you need to do is to call toDevice. So for example, in this case, if we have a GPU device available, we will just call model.toDevice, and it will automatically move all of the weights, all of these kernels and everything to GPU, and then we will calculate everything on GPU. Only the difference is that we also need to move the inputs, like the images, like pictures, also to the GPU, and then the ground truth also to the GPU, because we are executing the cross entropy loss function also on GPU. And then when everything is done, when the calculations are ready, then we move back the results from GPU to CPU using .cpu. Or you could also write, like, if we want to stick with the same syntax, you could write to CPU. This is exactly the same thing. So basically either that way or that way. So, but it's important, if you don't move back from GPU to CPU, it will again not work with, so you will not be able to convert it to NumPy and work something that is on this side of computer. So really simple way how to use this with GPU and CUDA, like really, really simple way. So here then regarding the dataset, let's look at the dataset. So I have the those Apple images, okay? So those Apple images are then loaded from my server and then pushed here, and then the output here in the self.x is basically self.x shape is the number of samples. There are a few thousand of apples. Then there is 3 channels, and then there is 100 by 100 dimensions. And then the output of the y, which is the classes which we want to predict, like is what kind of class of apple is this. Then this is like just 5 dimensions like that. So, and I also normalize the x, so this would be from not from 0 to 255 like in a color image, right? But instead this would be from 0 to 1, right? So this is what we normalize here. Then we split the dataset in training and test the parts. Okay, so like that. And then so my computer is a little bit slow now. Really hope that it will not hang. If by any chance my computer hangs, then keep on the YouTube and I will get back. Yeah, if you, I see in the chat you have only Intel graphics, so it will not work with Intel graphics at all. So, but it's fine. So so it's here. This function will execute only if the you have NVIDIA GPU. So if this is not true, then you will run it on CPU. On my computer, I also don't have working NVIDIA GPU. I have quite old MacBook, and basically they don't support it anymore. So I will run it on Google Colab, and you can also run it on Google Colab, and it will be great. So just a second. Yeah, Google Colab, right. Okay, so here we have the convolutional function. So, and here we have actually the calculation for that output size. So let's first implement the calculation for the output size. So the calculation for the output size is exactly as on our Jamboard. So let me find that calculation. So there is the in size plus 2 multiplied by padding minus kernel divided by stride, right? There is something missing. Divided by stride plus 1. Plus 1 divided by stride plus 1. Let's just keep it more clear. Add here these parts. And then also, if something is not dividing equally, let me check. Right. So if this might not divide equally, so in sense, so we could use math, or we could just use integer. So that would be better. So the integer will do the floor. So it means that it will pick the lower value. So if I have like divides by 0.6, it will give me a 0 value. So basically this is a floor value. So what it means is that if I have something like the output will be, let's say 32.6. So then after integer 32.6, we will get out the floor value, which is 32. So that's what will happen here. Anyway, so that's what we have, the formula for calculating the output of the image size after applying the convolutional function. So I will drop this on the slide number 9. Slide number 9. And now let's look at the convolutional function. So the convolutional function, I will give you some template here. So we have the input channels, we have the output channels, we have the kernel, we even have predefined the parameter, or this, remember the torch and end parameter, what it is. This is exactly the same as when we did with NumPy, the variable, remember? Variable in NumPy OP version, object-oriented programming version where there's variable with the value and grad, right? So in this case we have data and grad, and in this case this is just a like parameter of size. So this is a kernel size, kernel size with in channels, out channels, and basically this is a little optimization of what we've seen on the Stanford, this simulation of where you see the kernel slowly moving. So instead of just having, what we could do, so I'm just showing you what we could do. If you want, you can write it in that way. It will be like huge amount more work than using this method. So basically you could write it also like this, kernel 0, kernel 1, and so on. So this is exactly the same as in our images with two-dimensional nice kernels, and then apply it many times. So, but instead, the simpler method is to use additional extra 2 dimensions where we would encode how many input feature maps we have and how many output feature maps we want. And that is very nicely then done with the dot product. So the idea is that like if I have RGB, the color image input, and then I want to have two-dimensional output, as in the Stanford image that we just saw, where the nicely this kernel goes very slowly for the feature map, right? So in this case, this will be just in one line, much more simpler. You will see that in a second. So here, in forward pass, we calculate what will be the output size of our new image. So the idea is that if the input was this thing, then here the output will look like actually, so the out size, comma out size, and there will be the out channels as well. So this will be the output, and the input was the in channels with the in size, like that. So this is the input and this is the output of this function. Okay, so and then how to actually do this. So there are again many ways how to do this. We will do this in one of the most simplest ways possible, using for loops. Otherwise, if we just do it using more automated ways, it will be too confusing, or if we try to already reshape it. There are, at least I'm aware of few functions where you could like cut this code much shorter, and but then also there are these convolutional 2D functions built into Pytorch already, but we will not use built-in functions today. You will use built-in functions as your final homework. So it will be really fun because you will not need to write all of this forward pass. You will just need to build really cool and powerful models using the built-in functions. But if you don't understand how they work at all, then it's like completely useless to try to use built-in functions. So here, let's try to understand how it actually works. So first of all, as you saw that in the image, there was this gray part of padding. So let me jump back to the here. So you see there is this gray part of padding, and we say I want to pad by 1, but I could pad also by 2 or 3 or 4, whatever. So this is something what I want to add here. So, and then to add the padding, basically what it means is following. So we should create a new matrices with this padded size. So let me think. So, okay, so X, and so what we had, the in size, so in size pad, so this will be padded in size. This is really simple to calculate. In size plus 2 times padding. We want a padding in both sides, right? Really simple. So self padding, right? So in size pad is done. Then let's write X pad. So this will be X padded, or let's call it padded like that. And then here, this will be torch zeros. And so we're defining the empty matrix. This will be batch size. Similar way, actually, as we define output here. The output is already pre-configured, so we know what will be the output. We will also pre-configure what will be the padded size here. So this will be the batch size, then self in channels, which we know. Then we know self, in channels padded, right? So yeah, so this will be then the X or in size pad, right? So this is the padded size here. Also, comma in size pad to device. So again, I'm moving this matrix to device. So if I'm running this on GPU, I want that this matrix is placed on GPU, not on CPU. Otherwise, I cannot multiply together or do mathematical operations to two matrices which are on different devices. If one matrix is stored on the RAM and on CPU side, another one is stored in GPU memory, I cannot multiply them together. That's why I'm moving to device. So that part, then we need to store the inside xpadded. So xpadded right now is just a zero matrix, right? So what I want to do here is to store there the x. So comma. So this syntax means store everything from 0 till the batch size, store everything from 0 till the in-channel size, and then I just want to store specific area. So, and the specific area is following, so self padding. So I want to store from starting from padding till starting to minus padding. So padding, so on this part actually means basically length of the image in size minus padding, basically. So this is actually in size pad minus padding. That's what it means. So you could rewrite the same syntax here using this thing. This would be exactly the same output, or like that. So this one. Again, this code works specifically because the image is square, where the width and height is exactly the same size. But of course, the convolutional functions can work with non-square images as well, or non-square data, right? So it could work with like where there's this rectangles where one part is larger than another. Anyway, so that will work as well. So here then x should be stored inside this part. And if everything is correct, then this line will work just as it is. If the calculations of the sizes are not correct, then this line will not work. There will be an error that you are trying to put one matrix in another position where the size do not match. So that is one part. Then let's keep working with the other part. So let me think. So there is the kernels. What we have here. Okay, let's start building the loop. So this will be I out. So this will be the one output dimension. Then for I in range from 0 till, so we will go from 0 till, let's see, so x or the in size padded minus so more minus self kernel size. Let me think about it. And plus 1, I guess. So, and then self stride. So this is another part. So this is, we are moving this kernel slowly by the steps over this image one by one. So this is one part. Then the other part is j out, which will be the y coordinate, right? So we're going down, not on from left to right, but from top to down. And here we just copy the same thing. And I think the only thing that's needed to be changed is j here. So we just copied exactly the same part. So that's really nice. Then let's see what else we have here. Okay, so then let's cut out the middle part. So x part, so this will be a middle part which you want to cut out. So x padded, we will cut out again all of the batch, all of the channels. And here comes the interesting part where we cut out the small rectangle inside the bigger rectangle. So I, and then I plus self kernel size, which makes sense. Basically, this is exactly the same what's happening on that simulation on Jamboard, right? I, then here the j. So we're cutting out this small rectangle. So this rectangle is cut out here. And then what we want to do is we want to execute the, we want to execute the kernel function, in this case, the dot product, where we summate everything together, right? And then we will store the output inside just in one cell. So remember that the output is stored just in one small cell. So, and then for the output, what would happen is that out, we will store something inside in all batches, all channels, in I out. So this will be small cell here, and then J out, small cell here, and here we should store the result. And the result is something that is not yet calculated, so we will add that a little bit later. And then here below we need to add the j out plus 1, and here I out plus 1. So of course you could write this a little bit the other way, but in this case the idea is I think quite clear that we are moving very slowly one by one cell in the output image, right? And from the input image cutting out these small squares, right? And the input image is actually the padded image, so with the zeros around it. And now the only part missing is this middle part with the result. So on that we will code just in a second, but I just want to check that you are so far done. So our code is code ready so far, plus minus if you have some problems, copy some errors or so on. So I'm waiting for the confirmation and then we will move on, because otherwise I don't want you to leave behind too long. Okay, let me know when this is ready and then we will move on to the next part. So I see two pluses, really hoping that somebody else is also doing this. So is someone still working on it? Okay, I see three pluses, that's great. Someone still working on it? Without those three people, is someone still working on it? If not, then I will move on. And later it will be maybe harder to catch up, so it's great if you can be all on the same page. So wait for some answers. If no answers, then I will move. Okay, thank you for the information. I see that you're trying to catch up. Maybe to make it a little bit simpler, I will put this on the Jamboard. Of course, this is not complete code. We still need to write the actual kernel function inside there. But I just wanted to make sure that you get so far before we do the kind of the most essence and maybe the little bit more complicated part in the middle. So I'm dropping this also to the Jamboard, and I see that Vipin is saying about line 81. What is about there? Oh, you mean this one? So this is like the most simplest part. So this is just the calculation of what will be the output size based on the parameters of input size. But okay, so this is also included in the Jamboard, by the way, on the slide number 9. So it's much easier to look at the Jamboard. So anyway, so you should do this. I will wait again, so I will write down again the question. I see that you said that you're still working on it. I will wait. So please submit plus or some error when you're done. And those like Elena and Muhammad and Sharil can try to implement the middle part themselves. So if you could I don't like you could test it using some dummy data, but yeah, you could implement it yourselves as well. At least try to think about it, how it would work, because if you think about it, so the kernel is the so what it is the so it's the kernel size comma kernel size in channels out channels. Maybe just to make it simpler for those people who want to attempt to do this is following, so that to do the dot product, remember dot product works with the last 2 dimensions. It does not work with 4 dimensions and so on. So to make this dot product work on those last 2 dimensions in meaningful manner, the only way how to do this is following. So let me write down that one extra line. So the k, so we will change the shape of k to make it uh, resemble the dot product calculation, which will be in the middle part. So here this should be a 2-dimensional matrix, because we don't want to mix those higher the kind of what it's called, like, so the first dimensions inside that calculation, we just want to use the so we actually, in this case, we want to mix them all together and use it as a like 2-dimensional matrix as it would be in linear layer. Now it does not work like in linear layer, because there is the kernel by kernel by in by out. What I want to do is to make it more simpler. So here will be out channels. So this will be one part. Okay, so actually this is not good, I think. Let me think. Yes, it's definitely not good, because it will change the way how it looks like. So let's write it a different way. So there will be the kernel kernel size multiplied by self kernel multiplied by in channels, yes, self in channels, and then this will be comma this, or this could be rewritten even more simpler. And by the way, at the end we should be transposed as well. So, but it could be rewritten even more simpler in a way that you could just write all of this stuff as -1. So it says that, so this is the long way how to write it, this is the short way how to write it. So basically all of the rest of dimensions multiplied together goes in -1, and then at the end the result channels, and then we transpose it. So that's about it, what's necessary for this thing to work. And then the result part is something you can try to attempt. So meanwhile, while waiting for others to catch up, like those few people who did it already can try to use the kernel function there, try to reshape the y part so that it would work as the result. So you need to also reshape that y part, and that's it. So I will wait for others to confirm that you're ready to move on, and then we will implement these two last lines here, basically, using the reshaped kernel function. So this is now two-dimensional. So this is actually the so this is two-dimensional weight, right? So the two-dimensional kernel weight, which we want to then apply to something which is in y part. Okay, cool. I see that another person has finished, so that's great. Let's wait for a few others and then move on. So Randa can also then implement this line. Uh, Done with the previous now, line 100. Yeah, so you should do this line as well. So anyways, okay, so I assume that we're ready to go. So the last few things that need to be added here is following. So first of all, okay, we have a two-dimensional reshape, or the changing the so putting together dimensions in a way that this is a two-dimensional kernel here. And then this guy is unfortunately not two-dimensional. This guy is batch, comma, kernel, comma, kernel size. Basically kernel size, comma, kernel size. Actually, even not that. This is even more complicated. This is in channels. Channels, comma, kernel, comma, kernel. Again, just to reiterate, what was the upper one? This guy. So this is. Oh, come on, seriously, I did not copy that one. So this one instead is in channels multiplied by this, comma, out channels. And in this case, you can easily see, so this is again kind of very simple coding analogy that you can see here, is that these three are the same as these three, right? So, and if these three are the same as these three, why not then put them all in one dimension? So instead of having something like this, let's make, so the green parts you should not write, those are just comments, right? So If we could make it as this, so it will be the same way as above here, right? And to do that, again, this is very simple. So x part is x view. So in this view part, we need to have batch size, which we took from upper part here, because batch size can change, of course. And here lesson says -1. So that's it. That's it. So now we have batch. So what at the end we have here is following. So the k shape is the let's call this as a z. So let's write another line here. So so the z will be just this multiplication of all of these other dimensions. So the k shape is z comma out channels, and then the x part shape is actually the batch comma z shape, right? We cannot do the dot product between those two matrices because they are not the same shape. We could try to translate them around, and then we will end up by like mixing in batch dimension. So I don't want batch dimension to be part of last two dimensions. This is exactly the same thing we talked many times before regarding the kind of when we made the object-oriented NumPy, and also I think when we made the Pytorch version of the classification and linear regression tasks, is that dot product works for the last two dimensions. Let me write it down. Dot product works on last two dimensions. We never touch batch dimension. Batch dimension is something we never ever are allowed to touch. If we start touching batch dimension, we are starting mixing in samples themselves, not the features, it doesn't make sense at all. So instead, what we need to do here is to add additional dimension here as one, so this doesn't change the data. It's just like adding additional square bracket around it. So you can imagine again what it actually means is that if I have something like 1, 2, 3, and then 4, 5, 6, and this shape is of course so this shape is then 2 by 3, right? So this is that shape, and if I add additional dimension like that, it just means that I'm adding these square brackets around every element here. The data do not change, only the shape changes. And the shape is important because the algorithm of the dot product, what you implemented earlier on in this course, it affects the output, of course. So we want only this to work for the last two dimensions, not for the batch dimension. So in order for this to work, then it's really simple. So again, the green parts is something you should not touch. So the green parts just are for the comments. So here then we will have the k, and this is again the @ symbol, which means the matmul function for the torch and for the NumPy as well. So x part, and x part we will then unsqueeze with the dimension -1. So we are unsqueezing it, making it larger here. And basically it's just adding that extra dimension at the end, -1. I could rewrite exactly the same stuff by giving like dim2, because first one is 0, second one is 1, then this is dim2, but -1 is just more generic. So and then at the end we need to squeeze it back, squeeze, because it will produce the output. So in this case, if we try to do the dot product with this guy, so z z, then the output could be something like batch comma out comma 1 or something like that, or 1 comma out. And in this case, then I want this to be just b comma out. So that's why I'm squeezing it. And then if I have b comma out, that I can easily put inside this part because these two first dimensions are exactly what we get out of this result. I hope that this code works. I will quickly do some checks here. But anyways, so this is what needs to be done. I will drop this also full code to the Jamboard. I will highlight a few parts here which I just added, and try to explain why it works. I really hope that at least some of you understood it. So I'm adding those few parts. Of course, you can rewrite this same code with an additional for loop. Like if you imagine there is a next for loop which goes over the in channels and generating those out channels. So you could write it in that way and then just use, so it will work as well. But in this way, it's a little bit more simpler. Like otherwise, it'd be like a huge amount of code. So I added that to the Jamboard as well. So this is on the Jamboard slide number 9, I think. Yes. So as soon as you're ready, you can submit this task in the Google Classroom as a finished task. And meanwhile, I will quickly do some checks here. So one check that I want to do is just to make these dummy checks. So x dummy torch random. It should be like that. Oh man, didn't I include random? I hope now it will work. So torch random. Yeah, so oh, it was already there. What's happening here? Maybe it was a different name of the function, sorry. Yeah, around n or something like that. So this will be then the size. So the size will be some kind of batch size, comma 3 channels in, comma 100, comma 100. Then we can make a dummy convolution, conv dummy. This will be conv2d, and then the input parameters will be in channels will be 3 channels, out channels will be as in that example 2. Then the kernel size, let's say 3, the stride, let's say 2, the padding, let's say 1, and then we can get the output. Out dummy is conv dummy forward x dummy, like that. Then exit. Then I will add a breakpoint here just to check that this code is working, you know. So debug, just to make sure that I didn't give you some mistakes here. So yes, it did not work. So there's some small mistake, I guess. Let me check. The reshape function. View size is not compatible with tensors size and stride. Use reshape instead. Okay, sorry. There is one reason why sometimes you need to use not view but reshape. So please change it from view to reshape, because sometimes when in your RAM memory you store matrix in a format where these where it's like in a continuous manner, like the rows and like the columns and rows are arranged in some pattern, then if you want to change that shape, sometimes it's necessary to not just change assign the new pointers, but you actually need to copy it to new memory location in RAM. And if you need to copy in new memory location in RAM, then you use not view function, but you use the reshape function in the torch. So it actually gives you the error inside. So I changed this line, so you should change it as well. And if you see in the running here, it says that please use reshape instead, not view. And it's really simple fix here. So I please do change that line. So now if I run it again, let me see what we get. Hopefully we get it work. Yeah, it works. So it works and output dummy, out dummy, where you are, out dummy. So out dummy is 128 by 2 by 50 by 50. You see really cool effect happening here. The output is twice as small as the input now, just by having padding 1 and stride 2 and kernel size 3. So when we get output 2 times smaller. So you can imagine that by using some of these configurations of the kernel size and stride and padding, you can get all sorts of interesting outputs as well. So just for example, if I drop here 0 and change this to 4, let's see what will be the output now. Of course, you can drop all of just that inside the calculation of that function we wrote, or okay, now now there is a problem. Okay, very funny. So that's good that I checked this. So -0. Okay, there is a problem here. Okay, this is very good that I checked it. So if the padding is 0, this code is not good. So that's why I should add here this in size pad minus padding instead. Then it should work. Let me check again. And if this will be the case, I will update also on the Jamboard these few lines. It's really good that I tried to change that calculation. Okay, now it works. And the output is not exactly that word I wanted. So if I add padding 1, then it will be what I wanted. So it will be also reduced by 2. So anyways, here, this line should be also fixed. So let's add also a small change on this line. So there's three lines which should be carefully changed. The line 115, the line 117, and then in the middle part of the for loop. So I'm dropping those here in the Jamboard. Yeah, and then you can submit the first task as well. So let me ask in the chat. So is this code done? Plus minus, and then we will move on to actually trying to use this convolution to learn the classification of images. So on dummy code, you can use dummy code, but if you carefully write this code, and then it should work. But of course, the dummy code also might be useful. So maybe I will drop the dummy code somewhere that you can get it. Let me think how I could do that. There was the gist part. Let me check. I will create a, like, just share with you this small dummy code somehow. Okay, I have gist code. So anyways, so my question is in chat for this part, and I also drop you here the link to this small part of dummy code, so you don't need to write it yourself. I want you to write the actual code for the model yourself, but the dummy code is available in the gist. So let me show you what I mean by that. Here, if you open the link that I shared you in the chat, you can copy this dummy code in your code, and then you can basically check it out. That if you don't have some bugs there. So this is shared also for you. So I'll wait for you to confirm that everything is working so far, and then we will move on. Please confirm in the chat when your code is working. If you have some errors, bugs, please let me know. I can try to help you out. And then the next phase will be we will try to make that this convolutional network works on recognizing those apples. And basically, we will later implement some other functions, but using this function, you already can classify the apples, which will be quite cool. Okay, I see some question in the chat. So 100, 120, so 4J in range, Python input. So the thing that you call the error that Andrew copied in the chat is not complete. I cannot help you with that error if you need to complete the actual error message with all of what's there. Otherwise, it's I cannot really help, or drop it in gist as I dropped my code on the gist. So in that way I can help you out. If you can drop your code in the gist or the error in the gist, then I can help you. So still waiting for confirmation that we're ready to move on. Are we ready to move on? Plus, minus, if there's any other problems, please let me know. You can debug this code and explore it a little bit, but we should move on. Yeah, I see 1+ in the chat. Thank you. Google Colab, I think it should work in Google Colab, but of course it's not yet finished code. You know, it's just like there's only this part ready. So I will try to run this on Google Colab as well now. But it might be situation if you have NVIDIA GPU and if I have some bug regarding the GPU, maybe then it would not work. So I will try to run it on Google Colab. So on Google Colab, the idea is following. So you copy your code in this cell here. Then you choose the runtime, change runtime to GPU. Press save. By the way, there is also a library for Pytorch to support TPU, the tensor processing unit. So then connecting. Initializing. Okay, now it's connected. Then if I try to run it, first it should download the dataset. And then it should get to that exit line. So the exit line kills the app. Let me see. I have 2 pluses in the chat. So it's now downloading dataset. So and then I think it just exits if it works correctly. If there is no error, if there is no errors, then it will just exit nicely. If there is an error, then it will not exit. Okay, there is an error. Okay, cool. So device is not on the same. So see, this is exactly what I was talking about before. If you're trying to do operation between device with the tensor which is located on GPU and CPU, it will not work. And maybe if you have actually that situation on your computer, it will be that situations here as well. So here what's happening, K, so K, and why exactly it is on device? Ah, right. So I forgot to add here in the dummy code. In dummy code, if I add here to device here on the dummy code, then it will work, I think. So let me run. So the what it actually does, this dummy code here to device, it means that I'm moving the parameters, the learnable parameters from convolution 2D to device, and that's why it works. Okay, now it actually gone even farther away and try to do crazy stuff here, which I don't need to do. So stop. Anyways, the exit does not work in the Google Colab. So anyway, okay, so that's how far it works. If by any case you have the GPU based version, then you need to add here to device. That's it. That's it. Okay, cool. So I have at least 1, 2, 3, 4 or something like people ready to work. So then I'm commenting out this part. And then let's move below here in the model. So and let's construct some simple model here. So the simple model that we want to construct here is following. So convolution 2D. So the convolution 2D, and we will add here. So this will be our convolution 2D, right? This will be then in channels, which will be 3 in channels, the RGB, right? The out channels will be, let's think. So if you have 5 classes coming out, what we could do, normally what people do is they try to make larger out channels and smaller size these feature maps. So let's say 6 out channels, and then the kernel size. Kernel size will be 3, and then the stride will be 2. So we will try to make it smaller, padding smaller 2 times basically. So padding 1. Okay, and then the next layer will be built-in torch and relu. So the relu function is something that you already used in your homeworks and stuff. So we can use this one. Then for the next layer, of course, we need to use the previous in channels. So this previous out channels, this was 6, 12, like that. So very simple stuff. Then again, the relu and convolution. Oh, come on. Relu convolution here from 12 channels to, and we could leave it as a 12 output because basically we could also not change the channel count. It doesn't matter actually that much. So usually you could expand. Okay, we could. Let's keep it to 16, whatever. So anyway, so then we need to calculate what will be the size of in features here because the in features size for the fully connected layer cannot be determined just like that. We need to use that formula, remember? So what we could do is we could calculate out1 will be the get out size from actually this would be nicer if I would be able to use those values directly, but anyways. Okay, so let me see what was there. The out size. So there are these parameters. So kernel size is 3, then stride is 2, then padding is 1. So this is the same for all of them. The only thing that's different is in size, which in the very beginning is 100. Then in the second iteration, it's what's happening from the out 1. So we're using that one. Out 2. And then out 3 is taking the dimensions from out 2. Okay, like that. And then the in features is actually, because it's a squared, we need to use both of them. So we'll use the width and height multiplied together. So the width, what is happening with my clipboard? Width and height, and then 16, because the out channels are 16 here. So that's our in features for the linear layer. Okay, so I will drop this into Jamboard as well. So this is the first version of the model, basically. So the very similar to what you saw with this robot picture in the very beginning in the slides. So this is basically the same model. So I'm dropping this into the Jamboard. So this will be in the Jamboard slide number 10, the first type of model which we actually finished. So now I'm trying to run it just to check that there is no bugs on this side. So this is on the slide number 10. Okay, something is working, I hope. Not sure. While it's struggling here, I will just try to run it on the Google Colab, I guess. Oh, come on, it's really struggling here. So I will copy all of this code and just run it on Google Colab. Yeah, it seems to be working on Google Colab. So just to remind you again, the code is available here on the slide number 10 for the model. And in the Google Colab, it looks something like this. So the first accuracy is 29%, and it shows you that from the test set, it sometimes predicts correctly those apples. Sometimes it predicts wrong apples. So let's see for the slide for the epoch number 2, we have a little bit higher accuracy. So it's 42% for test data set. And now it's becoming better and better each epoch, and it works only because we know exactly the sizes of these convolutions. Otherwise, if we don't know the sizes, we cannot make the last fully connected layer, and it would break. We will talk about the last fully connected layer a little bit more in a minute. So now it's training and getting better every epoch. So let me know if it's working for you now. So is model working? Plus, minus, let me know in the chat. So now it's getting 61% accuracy, or yeah, 61% accuracy already. You can see that it sometimes mislabels red apples which are similar. So Apple Granny Smith and Red Delicious are two classes which it mixes together. But the green apples, it seems like that. Okay, it's interesting. Apple Granny Smith is also green. Don't know. Who knows why it kind of, maybe because some of the apples are on different angles. I don't know. So we'll see. So the accuracy now for the sixth epoch is 93%. So almost. So the 9 of 10 times the model is able to predict which apple is it like. So which species of apple is it? Or it's kind of not really the species, kind, I would say kind, I guess, or sort. Which kind of apple is it? So now on the epoch number 9, we get 94% accuracy on the apples. Now the error is with apple bare, bear, bra, what is that? Breborn and apple red delicious. So that is something it mixes together. So we get 95% accuracy even now. So really cool. It's kind of getting better and better and better. And it's not really converged even, because when it's converged, then you could see that the loss plot would be flattened, but it's still getting better. We're waiting in the chat to confirm that you get it working, and well, when you will get it working, we will improve upon this, make it even more better. So how are we doing? Do you have any errors, problems? If you have, then please use gist. So the same as I used in my previous one, I shared some code. Drop some code on the gist if something is not working, and let me know so I can help you. So we can see that the model is starting to converge. So at the epoch number 17, we get 98% accuracy, and the test loss starts to converge. So it seems like that the 5 Apple categories, it's pretty simple task. So what we could then improve is just make this to work faster. So you can imagine that if you would have like huge data set and then you would like to do the classification, it would be nice that your model would work much faster rather than just waiting like for 100 epochs to get the highest value. We will probably, with the changes that we will add to this model, we will make the convergence faster, hopefully. So I'm still waiting for the confirmations in the chat, and as soon as I will get some confirmations, then we will move on. Otherwise, like, I assume that something is not yet done on your side. and like it doesn't make sense just to keep moving if you're not ready. If there's any questions, if there's any errors, if there's anything like that, then please post on the YouTube chat, give the guest code for me, or like just interact so we can move on. Now we get 99% accuracy. It seems like for the small data set, we have solved it. The AI model can always classify correctly the apples, right? What kind of apple is it? But still, I don't see in the chat a huge response that you are like ready to move on. I only see one person saying that I guess the model is working on the Google Colab. would nice to see if others also work, would like the model work. So just to remind you, so in Google Colab, you create the new notebook, then you drop the code just in that cell, and you also change the runtime here, the runtime change type to GPU, and then you just start it. That's it. It's really that simple. So what's the problem? So let me know again. So I'm still waiting in the chat. Please confirm that we can move on. If I will not get any confirmations, I will just move on anyways, and then you will have homework. So that's so either interact in the chat, send me some problems that you have, or just confirm that you're ready to move on. So I see that Randa has some problem, but it'd be nice if you can share me on GitHub Gist some of your code, or so GitHub Gist, or just copy what is the problem. And previously Andrew also could just like copy that, and I can help you out live right now. Otherwise you will then deal with it yourself. So anyways, if you share me the problem, I will help, but otherwise I will now focus on the next part. So the next part is the other function that we see in the Tesla example in very beginning. So in very beginning, you see that in this model we have a function called pool, right? And you see that the output of pool is actually the same as an input, right? It's just a little bit smaller, basically. So this is another way how to reduce the size of this image. So you have the size of the image, and it should be reduced so that at the end we have some meaningful information. Okay, I see something. I worked with 6.2, but now shows problem syntax. Okay, I understand what you mean. So for the Randa problem, what it means is following. So in PyCharm, this programming environment, when you create a new file, you cannot just press run button here. You must press left click on this tab where you are editing this thing, and then press run here. Then you will run the code of which you are coding right now. Also in top here you see that it shows which code is right now running. See? And if you run the wrong code, of course you will get all sorts of wrong things. So that is your problem now, and hopefully you can resolve it yourself. I really hope that you can. So anyways, so we have the max pool thing that I just described, and the max pool is also like a kernel function. We will be able to copy actually the same convolutional function as for the conv2d, but in this case it will just do a little bit different result. So, and the little difference, what it actually does is following. So let me drop the example. So copy image is that you have some kind of input map and you have the output map, right? And the idea of max pool is using kernel. So in this case, kernel is 2 by 2, and the stride is, I guess, 2 most likely, or something like, yeah, in this case, if you're jumping by 1, so yeah, it will be stride 2, yeah, I think. So anyways, and then we will just select the maximum value of these guys. So the maximum value is here, the 6, and we will just draw copying here. And then for the backprop, when the error gradient will go through this matrix, it will just go through these few pixels. So here will go error gradient, here will go error gradient, here will go, and it will not go through the other parts. So this is one method of using, this is called max pool. You can also use average pool. Max pool can also be average pool, and all sorts of other types of ways how would you like to pool it. So so this is what we need to now build and include in our model. So let's, yeah, so I see in the chat that Randa resolved the issue. So again, I'm here to help. So if you share with me some information, I can help you. If you don't share the information, I cannot help you. So here, the max pool 2D. Okay, so I will also open the task for max pool 2D. So the task for max pool 2D is open now. So this is task 6.3. 6.3 task is open. 6.3 task is open. And here will be very similar stuff as we did previously. So I suggest that we just copy all of this code. So we copy all of what we had in the Convolution 2D inside the max pool. The one thing you see that we have the same parameters as we had in the Convolution 2D, but we don't have learnable parameters. So there's nothing that we learn in max pool. It's just reducing the size. It's not learnable. So that's very important to understand. Down here, so the K does not exist. So there is no learnable kernel here. So we don't learn the filter. We don't learn the kernel. So then here the result part. So let's think about it and look how it works here. So we also don't have the in channels and out channels actually. So in channels are here. Self in channels. Unfortunately, I use in channels here as well. So I guess we should. Do we use somewhere else? So you should not use the self here, just in channels. So in channels, that's good. What about out channels? Out size, we don't use out channels anywhere. So the in channels are here. So we will not change the shape of channels. That's why it's important to keep track of that. So we will not change the shape of the channels. Now we have this thing happening here, but we also want to keep the in channels then intact. So let me see. So batch in channels. So we will calculate the maximum value from these small rectangles for every channel inside the image. So for example, we will calculate the maximum value for the red channel, for the green, for the blue, for every of those small boxes inside our algorithm, where we go by the small filter box around all of this this image, right? So that's why I'm also selecting out the in channels here in this part. So far so good. Then we need to calculate the maximum values here. So the maximum values will be following. So comma this. So we will ignore the indexes. So the torch max function will return not only the maximum value but also the index. That's why I'm writing it as such, like this. So we are ignoring the second parameter. Then export. We could also rewrite actually this line, if you like, in this way, like a tuple. So it might make sense more probably. So export. And this will be over the last dimension, so dimension -1, like that. And I think that's about it, what we need to change here actually. So just to make sure that this is working, I will go back just in a second. We'll quickly just do some dummy stuff here. Okay, not like that. TQDM. Okay, finally somebody is giving some messages where. So TQDM is a library that gives you this small progress bar. So you can get it by this way. So you press in the bottom part terminal here. Then you write pip3 install TQDM, like in this way. And then you press enter, right? pip3, and it says I'm already installed this library. If you're not installed this library, you will get that library. So you will just open terminal and type in this line, like that. So very simple. Anyway, so here this should be working. Okay, if there will be some bug, we will fix it later. So I will now. Oh, great. Thank you in the chat that also Vipin helped out. I really appreciate when students help out each other during the live session. I do not appreciate when students help out for the homeworks and just copy from each other. So that is something that will get 0. So, but anyways, like in the live session, I really appreciate that you help each other with the questions and stuff like that. So copy paste is not learning actually. So okay, so here let's try to make sure that you get this max pool function ready. So I dropped this on the Jamboard slide number 12. So is max pool 2D ready? Plus minus, if there is some issues, let me know. And then afterwards, afterwards we will add this to the model, and then we will just look at the last function missing here, which is also a very interesting function, and that will be end for the day. And then at home you will be able to make really cool, like deeper models and more complicated models and do all sorts of things. Okay, while I'm waiting, I will do the dummy function. So where is my gist? I will do the dummy function. And then I will share it also to the gist for you. So, so the dummy function, basically it will be the same stuff as before, only the max pool would be max pool 2D, right? We could add 2 device. We don't need we don't need the in-out channels. So everything else stays actually the same. Okay, thanks. I see another error. So cannot be multiplied. I cannot tell from the message that you're giving. Okay, it seems like that's the last line. So from the error that you're giving me, it seems like that the in features here in fully connected layer is not calculated correctly for you. So you did not calculate correctly the in features for the last fully connected layer. The size should be calculated formula I gave you, and in a precise manner, like step by step. And then, of course, when we flatten, so the idea here is that originally we have something like batch, comma, 16, comma, out 3, comma, out 3, and in linear layer I cannot pass something like this. So instead I will pass in linear layer something which is flattened, right? Which is like made in just in 2 dimensions. So I multiply this, and then it works here because it's defined here. And if you have something something incorrect here, you will get that error what you got. So at least it seems like that's from there. Okay, so I'll try to run the dummy code for maxpool. I'll also drop the dummy code in gist for you. So the dummy code for maxpool is coming in. And yes, it works. It works without errors. So the maxpool works. At least I hope it works. So Just to double check, I will maybe add here a breakpoint and try again. I also want to check what is the max function. Yeah, the first value are values, so that's great. So this is correct. This is correct, hopefully. I hope it's correct, actually. Yeah, so these are the scalar values and these are the integer. I mean, like these are the floating and those are integer. Okay, cool. So this is correct. So in this variable, there is actually indexes of the maximum values. Anyway, so this is the 2D max pool, and then the max pool 2D should be used in this model formation here in the following manner. So if you want to make the same way as it was in that example of Tesla, so what we could do, we could actually look at how it was structured there even on the slide number 1. So yeah, it's after relu layer. So let's do that after relu layer. So we can add max pool, and I want to keep these formulas the same. So what I will do is that I will try to make that convolutions do not change the size. And again, this is very simple using that same formula. And if I would change the stride to 1, it will not change the size anymore. So that's really neat trick. So here, then I would add the same kernel stride and padding as before. Here as well. Here I will change the stride to 1. Also stride to 1 here. Now it will work nicely. Only the problem is that now this is a very long code and I want to share with you, so I will make it a little bit shorter, like that. So now we added the max pool layer, and hopefully it works the same way as before. So if there's no errors, it should work as before. So I'll drop this in the Jamboard just to check that there is no bugs as well, and just to see how well it runs. Unfortunately, there's something not working. Gradient incompatible shape. Something is not as it should be, but that's no problem. We will fix it. So this is 3 by 1 by 1, 3 by 2 by 1. We'll see what's happening here. So debug. Okay, what's happening? What's happening? Why it stopped here? Not sure. Doesn't make sense that to be stopping here. Running again. Seems like that there is some kind of bug. We will see what it is. Okay, now it works. Maybe I will also reduce the batch size so that it will work faster on my computer. So if I have the GPU, then I will use 128. If I don't have GPU, I will use batch size of 4, whatever. So let's run it again. You can also change batch size to 4 in case if you are running on CPU, and if you're running on GPU, then make a large batch size. I just want to make sure that there is no other errors here. It seems like that. Okay, now this is something wrong here. So the linear layer fails, which is very strange. Yeah, linear layer. Okay, so I have some mistake here, I guess. Maybe a similar mistake as Vipin noted, but at least this is because of the max pool, not because of convolution. So out size is the 16, 25, 25, and okay, but there is a stride 1, okay, stride 2, okay, cool, and out flat, 10,000, which is strange. Maybe it is not strange, I don't know. Anyway, we'll see. So, and then if I drop the other breakpoint here, so this was 25. So this error, I think we will fix it easily, hopefully. So here the output is smaller. Okay, that it's because I have actually just 2 max pools, not 3. Okay, got it. So, yeah. So what we could do, we could add one more extra layer, I guess. Okay, so let's make it just in one line. Paddings. So I have only 2 max pools, but whereas before we had 3 reducing convolutions. Now convolutions do not reduce the size because of the combination 3 by 1 by 1, but the max pools reduce the size now, which means that we need another layer like this. So then it will work, except here we need to change from 12 to 16, like that. And now it should work nicely. Yeah, so this will be fine. So I will drop this also to the Jamboard, so you can check this out. And create your model so that it will use the max pools. This we will move to the slide number 13, I guess. So slide 10, 11, 12, 13, 13, okay. So slide 13, we have the model. I will copy this and move to the Jamboard, put to the Google Colab. Google Colab. Oh, come on, what is happening here? Google Colab. Copy, paste, run. I hope it will work on Google Colab without any problems. Really hope. So now it's running backward pass on the Google Colab. Yeah, it's working. So it's now working a little bit slower in Google Colab because now we have more complex, more deeper model, but still it's better now. So we'll see what is actually, I don't know, but so if it's better, we'll see what is the result after the first epoch. And meanwhile, I will wait for you to complete this model changes. So the model is here as well in the Jamboard. So this is the task. I think it was the task 6.3. And it's slowly executing the model here. While it's executing the model, I just want to talk about the last function before we end today. So the last function is called batch norm. So there are different kind of normalization functions that you can try out. Historically, there have been even more, and I think there's even more new functions for normalization coming out in recent papers. So the idea is here is following. Because we are working just with small mini batches, there is a high probability that in somewhere in between your model, like if its model is very deep, then the like features will be very offset in some direction. And this kind of function tries to, like the same way as you remember, so this equation should be very similar to what you already have seen many times. So this is standardization function. So this is like making the x in the middle of the zero, you know, like in the plot middle, right? So this is subtracting x by the mean value and dividing by standard deviation, basically. And the kind of like idea of this situation is following. So if we imagine that we have ReLU, and this is like inside somewhere deep inside of our model, right? And we have some data point here, and previous layer shifted all of our data points somewhere here. And of course, if you know ReLU, then it will ignore everything that is on this side of the nonlinearity. So this kind of batch normalization and all sorts of normalization functions try to move these data points to the middle so that they would make more sense for the model. And of course, this is a little bit more difficult task because we cannot just move one batch to the middle because then it would like kind of destroy all of the learning with regards to other batches. But instead, we need to predict which is the middle point for all of the data set. And to predict the middle point for all of the data set, we'll use gamma and beta. Those two are learnable parameters for scale and shift. And basically, if you learn those, then every time when you are deep inside your model and something is shifted very far left, you will get it very nicely aligned in the middle part. So that is the equations for the batch norm, batch normalization. It works best if the batch size is very large. If the batch size is very small, or if the batch size is 1, then it's very bad. So basically, that is what it is. So yeah. So let's see. I hope you're able to make the model with the max pools. So what is the result here? Okay, so after the first epoch, we get 33% accuracy. So that's not bad. It keeps training. We'll see how it progresses. Anyway, okay, so let's implement then the batch norm as well, because we don't have any more much time. So I will open the task 6.4, which is batch norm task. And here the task is following. So we have the gamma, beta, mu, sigma. I think even this task you should be able to implement yourself quite easily because this is not a like complicated convolutional function. This is the most simplest function which you can imagine here. So basically, this is very similar to what we did with the ReLUs and stuff like that. So here, then we need to calculate the mean. So this will be the mu. Mu will be x of mean, or let's say torch mean, mean value of x, and then we need to think about dimensions. So we want to calculate the mean values with regards to each of the channel dimensions. So here are the num features, the channels for which we are interested. So we ignore what we ignore. We ignore the go over each channel. For each channel, we calculate one value. So we ignore width and height, basically. So we ignore width and height, but we need a batch. Batch is something which stays untouched. So batch stays untouched. Then we want to calculate the mean value with regards to middle part. So one option is to do following. So dimension. So I don't want to touch batch dimension. I want to use the second dimension, which is channel dimension. And I don't want to touch the 2 and 3, which is width and height. So we will use that. And then we also can keep dims just to make sure that the matrix looks the same, but the data is not changed anyways. So that part is fine. Then with regards to the variance, or the sigma squared, basically. So sigma squared. So sigma squared is so this will be the, again, torch mean, but inside that part we will have this small function. So the small function is actually the x minus mu, x minus mu squared, right? So this is a kind of squared error here. This is a squared sigma, basically, whatever. So anyways, and then we have the y x prime equation. X prime equals the x minus mu divided by the square root torch sqrt of sigma squared plus epsilon e minus 8. And then the output is those learnable parameters shifted. So the learnable parameters which are shifted is following. So okay, I think I messed up something a little bit. So I calculated these guys. Why do I have it here actually? I think there is something not necessary. So these things are actually not necessary here. So these are definitely not necessary there. Okay, cool. So the output then is the self gamma multiplied by x prime plus self beta. There is no matrix operations here. There are just like pairwise operations. Okay, so this is what we have here. Then I will do also a small dummy function and share your gist also to here. So let me copy this one. So there will be a dummy function. So this will be dummy. Okay, so this was con, but anyways, so this will be norm dummy. Norm dummy. Batch norm 2D. Now that there is the necessary for the num features. And num features is basically the same as the input channels. We are normalizing across each of the channels. Of course, you can easily think of other ways how to normalize. You can normalize across the width and height. You can normalize across the width and height and channel. So there are different ways how you can normalize it. It's not just this only way how to do that. So here, let's say 3. So, but that would not be batch norm if you do what I said just. So there is also a group norm, instance norm, the layer norm. There are like all sorts of other normalizations. So now if I run it, Yes, it works. It works. It works. Great. At least I hope it works. So I will share the gist for you. And the model in the Jamboard, in the Google Colab, is already at 77% at the epoch number 3. So really fast convergence, basically. So epoch third is already having 77% with the max pool. So create this one, but it's slower. At the same time, it's fast convergence, but it works slower now. It's just because we're doing this manually without any optimizations, you know. So if you see here, we already are at 77% accuracy at epoch 3. So that's here. Then this was the batch norm. I'm now sharing in the chat the gist for dummy function. And then the last thing that's necessary is to add the batch norm to our model. So to add the batch norm to the model is by going down here. And where is the model? Here, right? So normally batch norms would be added before the nonlinearity, where it makes the most sense, but there are also some other alternative theories where to place the batch norms. So norm features, here they will be the 6 as it was here. And here it will be 12. Here it will be 16. And at the end, you could add it at the end, or you just leave it as that. So we'll copy everything and move to the Jamboard. I mean, also the Jamboard and to Google Colab. So the Google Colab version I'm killing and trying to run it again with the batch norms. Hopefully with the batch norms it also would work. So while it's running, we'll copy the model code for you in the Google Colab. It's a little bit slow. Anyway, so this is the model code, and now it's slowly getting through the first epoch. And the model which we just created is it's sometimes also referred to VGG. So there is also a pre-trained model which you could try to use, which is also called VGG, and it's basically the same kind of architecture what we just did. So I'm also assigning now the homework. The homework will be just to create similar model as we did now, but using the built-in functions in Pytorch, which will make it a little bit faster and simpler. So I think you should be able to do that quite easily, just to change it from what we did now together in a manual manner to a more automatic manner where there is already accessible some of those functions. If you want to, you can create more complicated models than what was listed in the schema that I gave you in the homework now. We'll wait for the output here, and then we will end this session. Hopefully we will get some nice output. So what about the Okay, I forgot to add also the actual patch norm to the code. I really hope that you can do it yourself. If you try to do it first yourself, and if something not works, then you can watch here. But I prefer that you not just rewrite the code from here without thinking. So it's still working here. Okay, with this model, it's super better. So you see, after first epoch, we get 65% accuracy. That is just after first epoch. So you can imagine, like in 3 epochs, you'll get 100% probably. So you see, this model works so much more better just by applying a little bit of knowledge how to do this correctly, right? So yeah, so that's about it for today and for this mini course. So this mini course was done in collaboration with LiepU University and my research group. And so basically, if you so to pass this course, depending on your university's policies, you should get at least 40 or 50% of the mark. You can get that easily if you just finish all of the classworks and not the homeworks. And the classworks you can do in the monkey style just by trying to copy what I'm showing without thinking even. But if you think, then you are able also to do the homeworks. If you do the homeworks and if you achieve the result of 90%, 90, or higher, then you can try to contact me regarding the supervision of the thesis, where you would need to learn a lot more in this direction before you could actually start building any kind of scientific value models. So that was interesting experience working with you. I hope that we will meet again. And yeah, so this will be end for today. And you will have about like 2 weeks to finish all of your works, and then I will send the final marks. Okay, so that's it for today. And please do not copy the code from each other. Like it will just and you get you zeros. So that's it for today. And hope you liked it. Hope you learned something, and hope it was really interesting. You see, the deep learning and AI models can do crazy things, and this is just a very small part of everything that's possible. What we just covered, we normally cover about like 4 or 5 times more information. So that's about it for today. Bye bye.